Hi everyone, this is day 2 of your limiting reagents lab, and today we have a great warm-up. We are going to show you how to do the math on the handout that we gave you guys. So part of the warm-up question that we have today, question number 1 for the warm-up, is what is molarity? Alright, so what is this word molarity? This is something new. And it's something that I think you guys might have some background knowledge of. Do you guys remember when we were working with the micro rocket lab and I told you that my hydrochloric acid comes in 12 molar? Do you remember me saying that to you? But I diluted that down to 4 molar. You guys kind of remember me saying that? Molarity and molar are kind of like the same thing when I say those words. And what I'm talking about is concentration. That's what molarity is, concentration, how concentrated the solution is. It's another word to mean concentration, how concentrated it is. But it also has a symbol, and so anytime you see the symbol, you'll know that they're talking about concentration. The symbol is a capital M. Capital M. That's the symbol for molarity. And what molarity is, we're going to actually define it now. Molarity is the number of moles of solute, that's the stuff that gets dissolved, number of moles of solute per liter of solution. So it's actually telling you how much stuff there is in the solution, how concentrated it is. It's a numerical value. So if you have your handout from the lab, pull that out, and I want you guys to go to page 2 where it lists your supplies. And the very first 2 things listed were the reactants that we were working with. Okay, so take a look. You were working with barium chloride, and you were also working with potassium iodate. What is the concentration of those solutions, both of them? 0.2, and you see a capital M, correct? That's what M is. It's molarity, how concentrated it is. So if I had 1 liter of solution, it would contain 0.2 moles inside of it of, barium chloride or potassium iodate, because they're both the same concentration. All right, so that's one of our warm-up questions. The other warm-up question is, what is this? Because it's on your handout. MMOL. All right, you ready? This stands for millimoles. Millimoles. And you're like, millimole, what's that? Well, what does the prefix milli mean? It's a very small fraction. Do you guys remember the fraction for milli? 1/1000th of a mole. That's what a millimole is. 1/1000th of a mole. Alright, so you guys already know what a mole is, but if you have a millimole, it's 1/1000th of a mole. And since we did what we call a micro-scale lab, that's what this is, since you're doing a micro-scale lab, we are dealing with really small quantities. Alright, everybody? Alright, so now go to stage 1 of the handout, and you should have some data there. So go to stage 1 of your handout. Make sure you're looking at the grid, the chart. This is what I'm going to help you out with. Oh, and if you left your, if you know you had your handout last class and now all of a sudden you don't, there were some handouts that people actually left in the lab. So I put those in the back of the room in the middle, right here, up on the top. So if you lost your handout, you may want to go check to see if you accidentally left it in lab, okay? Anyway, so in your handout, you have this first part that says millimole, right, MMOL, starting millimole of the barium ion, 2+. Sorry, I kind of made that wonky there. All right. And then the next part over says starting millimole millimole of the iodate, IO3, that's the ion. And then the next part over says expected millimole of PPT. That means precipitate, how much precipitate you made. And then the next section over says expected excess millimole. Expected excess millimole. All right, so there's the chart, and I'm going to show you just test tube A and B. Again, make sure you're looking at stage 1, right? And I'm going to show you guys how to get all of that, okay? All right, so I'm going to refresh your memory of the net ionic equation that you guys are working with, okay? So this was the warm-up from last class, and the net ionic equation kind of looks like this. It takes 2 iodate ions, takes 2 of these, and 1 barium ion to create your precipitate. Barium iodate. Solid. All right, so there's your net ionic equation. It's always good to remember that this is not a 1-to-1 ratio with your reactants. All right, that's going to help us out a little bit, okay? All right, the first thing that I want to ask is for test tube A, make sure you're looking at test tube A. How many milliliters did you use of the iodate? It was potassium iodate, but how many milliliters did you use of potassium iodate? You should, yeah, 3 milliliters, am I right? So you used 3 milliliters of this. How many milliliters of the barium did you use for test tube A? Was it only 1? Okay. 1 milliliter of this. Okay, everyone. So here is where we're going to find out this new thing called millimole. I'm going to try my best to explain what a millimole is and how you get it. Both of these solutions have what we call 0.2 molar. That's their concentration. They both are 0.2 molar. And so a millimole is 1,000th of a mole, correct? Let me show you. I'm going to show you this guy first. We're going to calculate the millimole of iodate ions, and I'll show you how that works, okay? Here we go. So molarity, if I have 0.2 molar, what that is that's the number of moles, that's the number of moles per liter of solution. Do you see how I did that? It did 0.2 moles per liter. That's what this is. I'm just showing my units. All right, you ready? All you have to do to calculate millimoles, you take the quantity, the molarity right here, and you are going to multiply this, see I'm multiplying, by the number of milliliters that you have. You had 3 milliliters. Now I want you to pay attention to the units. Pay attention to the units. You ready? Does everybody see how there's a liter on the bottom right here, and you're multiplying by milliliters on the top? Well, that's not a perfect cancellation of units, is it? Like liters and milliliters doesn't necessarily cross-cancel, does it? Okay, so think carefully. If I change this value right here to a liter, wouldn't that solve for moles? Right? The liters and the liters would perfectly cross-cancel, and we would be solving for actual number of moles. But what if I don't change this to liters and I leave it in milliliters? Do you see what I'm going for here? You would be solving for millimoles instead of moles. If I keep this as, think about this, how many milliliters are in a liter? How many milliliters are in a liter? Help me out there. 1,000, right? So in order to change my volume to liters, I would have to go like this. 3 milliliters, and I'd have to go like this. 1,000 milliliters per 1 liter, right? And that would give me my volume. See how these cross cancel? That would give me my volume in liters. And then watch this, watch this. If I keep going, and I've got my volume in liters, watch this. Each liter would contain 0.2 moles. Do you guys see how that's the molarity of the solution? This would actually solve for moles. That's what that would do. But if I don't do this part, would I be solving for moles? No, I would be solving for millimoles. I hope that makes sense. All right, everyone, so you ready? That's what I'm going to do right here. What is 0.2 times 3? Can you solve for that, please? You can do that in your head. 0.6 millimoles. We started with 0.6 millimoles of iodate. So come up to your grid. For test tube A, we were solving for iodate. This would be 0.6 millimoles of iodate ions that we started with. All right, so 0.6 millimoles starting. All right, everyone, let's do the barium. I think now that you understand the process, how do we get the millimoles of barium? What am I going to do to these two values? All you have to do is multiply. What is 0.2 times 1? 0.2. So over here, we're starting with 0.2 millimoles of barium. Okay. So now we are going to do some stoichiometry. We are going to predict and calculate the correct amount of precipitate that can be made. All right, so here's our starting material. For iodate, we are starting with 0.6 parts, if you will. We can call it millimoles if you want, but we are starting with 0.6 parts of the iodate. And then we are going to be starting with 0.2 millimoles or parts of barium. Let's figure out what the maximum amount of barium iodate that we can make given these two supplies. This is just like stoichiometry, huh? All right, so guys, there's two ways you can go about this. You can do that math in your head, not very easy, or you can try to do the math like in dimensional analysis, and that's what I'm going to do, so that hopefully people who can do it in your head, you're great, that's fine, I'm glad you can do it in your head, but I'm going to show you how to do that math. I'm going to actually show the math. Here we go. So I'm going to do some erasing. Sorry, hold on. All right, so if we start with 0.6 of the iO3 ion, okay, 0.6, and you see how I didn't say millimoles? I'm going to call them parts now. I'm going to call it what it is, because millimoles is what we use, like moles and millimoles is that mole ratio. That's the heart and soul of stoichiometry. So all we need to do are ratios with the millimoles. Are you ready? What is the ratio between your iodate and your precipitate? What's the ratio there? 2 to 1. Now, when you're doing this, when you're doing a ratio, you need to cross cancel. If you've got iodate here, what has to go down here? Iodate. How many iodates? 2. Look at that coefficient. You see the 2 coefficient? So we have 2 parts iodate for every 1 part of your precipitate. All right, you guys, what is 0.6 divided by 2? That's easy. 0.3. So that reactant can make a maximum of 0.3 millimole of barium iodate of the precipitate. Let's see how much this guy can make. Let's see how much the barium can make. So I'm going to set up my next one. We are starting with 0.2 parts of the barium ion. Let's get the ratio. Look at the balanced reaction. What's the ratio between barium and your precipitate? 1 to 1. So for every 1 barium, you will make 1 of your precipitate. Cool. What's the answer here? 0.2. All right. So what is the maximum amount of barium we can make? We have a reactant that ran out. What is the maximum we can make, guys? 0.2. Come up here. The expected amount of precipitate is going to be 0.2 0.2 millimole. That's the maximum we can make. Can I ask you to extend just a little bit? Which reactant ran out, the iodate or the barium? Which one is gone? Barium is gone. Did you use some of the iodate? Yes. Did you use all of it? No. So what I'm going to do now is I'm going to say, all right, this barium iodate, I know that I made 0.2 parts of this. The question that you need to answer is, if you made 0.2 of the precipitate, how much iodate did you use? Because you didn't use all of it, you only used some of it. I'm going to repeat the question one more time. If you made 2 precipitates, how much iodate did you use? Now you can probably do this in your head. Let's see if I can challenge you guys to do this in your head. You ready? If you have 2 of these, and it takes twice as much, you see how there's a 2 in front of this and there's only a 1 here? If you had 2 of these, how many of those did it take to make 2? 4. It doubles it, doesn't it? Now I'm going to show that work just to make sure you guys can see it, so you can refer back to this if you ever get caught and you're struggling to do your lab, okay? All right, so this is how we figure out how much iodate we actually used. Here we go. I know that I made 0.2 of my precipitate, barium iodate. I made 0.2. The question is, how much iodate did I use? Because I didn't use all of it, I used some of it. All right, you guys, what is the ratio here? Think back up here, look up, look up. What's the ratio in front of your precipitate? It's 1. What's the ratio in front of your iodate? 2. All right, so watch. I'm going to cross cancel. For every 1 precipitate, for every 1 of these that I make, I used 2 of these ions to do that. What is 0.2 times 2? 0.4. Now what does this represent? Oop, millimole, sorry. No, this does not represent your excess. Careful. What does this number represent? Yeah, that's how much was used. How much was used. Now, to figure out your excess, you got to be careful. You had 0.6 parts available. How do you figure out your excess? Subtract how much you used. How much did we use? 0.4. What is 0.6 minus 0.4, everyone? Guys, in this last box, you're going to tell me how much is excess, 0.2 is excess, and which one was excess, guys? Iodate. IO3. So please make sure you not only tell me how much is excess, but you also tell me which one was excess. Hey guys, just curious, look at your data. Did you get a positive result for the iodate ion as being excess for test tube A? Is that what you got? Yeah, and I looked at your guys' class data when you guys recorded up on the board, and I was like, yes, they did it right. So you're confident that you did this right. You just checked it on your math. Pretty cool, huh? All right, everyone, let's do test tube B to make sure you understand the process. All right, can I get the starting volumes for each of the reactants? And I'm going to redraw this so that it's nice and pretty. Hold on. Yields. Okay, you ready? Can you give me the starting volume, the amount of milliliters that you use for your barium? 3 milliliters. And what was the starting volume for iodate? Yeah, because the iodate was being held constant, am I right? Okay. All right, the concentrations on both of these were 0.2, correct? So how do you get those millimoles again, guys? What do? Don't you just multiply the volume by the molarity? So this starting volume or starting amount is 0.6 millimole, and this guy is also 0.6 millimole. So come up here and let's fill them in. 0.6 millimole, 0.6 millimole. All right, you guys ready? Let's figure out the maximum amount of the precipitate that we can make. here we go. So if I started with 0.6 parts of barium, we're going to figure out the maximum amount of precipitate that can make. What's the ratio between barium and your precipitate? 1 to 1. All right. And I'm going to abbreviate PPT if you don't mind. It takes a little while to write that. So this can make 0.6 of your precipitate. Let's do the next one. All right. The other one, you're starting with 0.6 of the iodate. And this time, careful, the ratio between iodate and your precipitate is 2 to 1. For every 2 parts of iodate, you can make 1 part of your precipitate. All right, everyone, what is 0.6 divided by 2? All right, everyone, what is the maximum amount of precipitate we can make? 0.3. So we can come up to our grid. This guy can make 0.3 millimole. So if you make 0.3 of this, let's see what you think. You ready? Who ran out? Who's gone this time? The iodate is gone. This guy is gone. So we used some of the barium, but did we use all of it? No. The question is, how much did you use? So we know that we made 0.3 of the barium. What's the ratio between your precipitate and barium ion? It is a 1 to 1. So if you made 0.3 of the precipitate, you used 0.3 of the barium. Now I'm going to make sure you guys can see the work for yourself. We made, this is how you figure out your excess, we made 0.3 millimole of the precipitate, and I'm going to abbreviate. We made 0.3 of the precipitate. The question is, how much of the barium did we use? Because we didn't use all of it. Ready? For every 1 part of the precipitate, I will need 1 barium ion. That means I used 0.3 parts of your precipitate. Oh, I'm sorry, of your barium. I knew what I meant. So we only used 0.3 barium. How much was available to us, though? Yeah, see? You had 0.6 available. And you only used 0.3. What's the leftover then? Gotta subtract. That's right. So we have 0.3 millimole of barium left this time. Make sure you switch that to barium. Hey guys, did you test positive for barium in test tube B for the excess? Swell. Isn't that great? All right, so this is an issue because we've never done this lab before. I've never done it before, and so I'm not really sure exactly what I want to look for in your lab report. And what I plan on doing today at the end of school is posting a rubric for you guys so that you can better do like kind of a check off of what I'm looking for. So I'm going to kind of go over that real quick. I want to make sure that you do a thorough job on the background section. So in the background section, go ahead and pull it and look at it. Did you show the net ionic equation? If you didn't, you missed that. That is very important information given in your background. You want that in your background. Did you guys, in the background, like if you look at the original handout, and I'm diving into, I'm checking it out here, there was important information that they gave you in the handout itself. Whatever they talked about, that's what you should talk about too. So from each paragraph in the background, which there's not very much, you see how it's just that first page, in each paragraph, you should probably be pulling something important out of there and putting it into your own words. So make sure your background is cool. Don't forget there was no pre-lab, so you don't have a pre-lab section this time, so you can say none. Nice. All right, for the procedure, reword all of this, and I had a question from one of my students. I thought it was a great question. They said, hey, Mrs. Crowley, do you see how, like on page 3, for stage 2 and stage 3, it says repeat? Can we do that too? Answer, yes. Go right ahead. All right, but make sure you are very careful about what you're repeating, and you are not numbering your steps. Just, if I were you, I would say something along the lines of follow the same steps by observing the data table available on stage 2 and stage 3 in the data section. That's what I would say. Something along those lines. Just say, look at the data table for stage 2 and 3 and make sure you're mixing those ratios properly. And follow the same procedure to test what is excess. Does that kind of make sense? Okay. And then after that, oh, we already discussed the hypothesis. Everybody still remembers the hypothesis/purpose statement because we did go over that in the pre-lab last class. Okay, so then after that comes the analysis. In your data analysis, this is what I want to talk about now. You have post-lab questions. Did you know that you have post-lab questions? All right, where are they located in your handout? What page? Your data analysis questions are on page 3. Do you guys see that? You have 4 questions. It says complete the following for each of the stages 1 through 3. Make sure you're doing each stage. Don't skip that out. Okay? You're not just answering this one time. You're answering each of these 3 times. Is that clear? Be careful. And then when it says, you know how like you're supposed to show your work for like the data analysis? I had a student say, hey, Mrs. Crowley, all of the stuff that you did here, like, do we have to show that for every single problem? No. I consider what we did right here sufficient work to show, like, at least 2 examples, you know what I mean? Show 2 examples, explain it. You guys know how I was explaining how to calculate the excess, how you want to check those mole ratios? Guys, that's totally fine to just show like maybe a couple examples and then the rest of it you don't have to show. But I can tell you from experience, me personally, I'm the type of person that when I'm doing a lab, you know I'm going to be showing my work for every single set. You know that I'm going to probably like write it out. That's just me. I'm a type A personality. I like to show my work consistently, being very careful and methodical, right? But some people just don't think that way. So I am allowing you to only show maybe 2 examples like this on how to calculate excess, because one of them gave you excess barium, the other one gave you excess iodate, right? I'm allowing you the freedom to just show me 2 and explain those 2, test tube A and B from stage 1, because everybody should be able to repeat those steps for all the other problems. Does that kind of make sense, guys? So in your background, if you're asking, do we have to show our work for every single one? No, but you do need to at least explain 2. This is the bare minimum that I would expect to see. All right, and we got some hands. Go ahead. The question was, if we show our work for every single one, do we have to explain it? Now, I'm going to tweak your question just a little bit. You need to explain at least 2. After that, you do not need to explain. Now, if you want to show your work, that's great, but you don't have to explain each and every one. Please don't. That would be a very long lab report. All right. You good with that answer? Okay. Any other questions on that? Are you sure? Yeah. No? Oh, sorry. Okie dokie. All right, so please be careful with the conclusion, or I mean with the data analysis section. Now in the conclusion, this is the easy part. The conclusion is meant to be short, sweet, and simple. You guys had 3 stages. For each of those 3 stages, you had 5 test tubes, right? All you need to report is what was in excess. That's it. So it'd be like stage 1, test tube A, excess barium. Or what was it actually? Sorry. Excess iodate. Test tube B, excess barium. Test tube C, excess, you see what I'm doing? That's your conclusion. You are just stating your results. That's it. You do not explain stuff in conclusion, okay? You just report it out. All right, now let's talk a little bit about critique and error analysis. Guys, you already did stage 1. What was, in your mind, the hardest thing to measure in stage 1? What was the hardest thing? And it may be more than one. All right, go ahead. The height of the precipitate. I 110% agree. That was the hardest part. And those darn rulers, I had some smart students in one of my class. What they did is they put the ruler standing straight up on their desk, and they brought the test tube